just like Simon said, I'm going to talk about reactive integrations with Akka streams that just work. The title was set by my colleague Konrad Malavsky, so no pressure on me from him at all. I will start with a short introduction of myself. I am one of the core developers in the Akka team, employed by Lightbend. Lightbend is the company behind Akka and Scala and Playwork. We have some other stuff going on as well. I would like to, I'm also a co-organizer of the Scala user group here in Stockholm. So we have a good roll of sessions going on every month or every second month with Scala specific topics. Yeah, as I said, I would like to thank Konrad for setting the title and giving me some pressure about the demos in this talk. He's also a core member of the Akka team, and he wrote the Reactive Streams TCK, and he's deep into the Akka persistence and Akka HTTP parts of Akka. So now I mentioned Akka a few times, but what is it? Akka is a toolkit, a library for building concurrent and distributed applications, and we aim to make that simple. Its core thing is actors, which is a concurrency model or an abstraction to build concurrent applications. Additionally, inside of Akka, we have a cluster and remoting for building distributed systems across many nodes. We have some prepackaged tools for doing things on clusters, such as a singleton that lives in the cluster and is kept alive even though nodes come and go, and cluster sharding, which distributes objects across the cluster in a clever way. We have streams, which is what I'm going to talk about today. And we have something called Akka persistence, which is about building event-sourced applications with Akka and actors. We also have a complete and fully asynchronous reactive HTTP server called Akka HTTP. We have a bunch of integrations, and we have a few that are official. So we have a Kafka connector, and we have a Cassandra driver for persistence, and we have a DynamoDB driver for persistence as well. And there's a huge community around Akka and a lot of third-party sort of projects that connect Akka to different things in different ways. Akka itself is written in Scala, but for every feature, there is a Java API. And for every new feature, there is a Java API from day one. So it's not like an afterthought, but something that we keep in parallel, so to speak. So you don't need to know Scala to be able to use it. There will be a Java API for all the things that you would want to use in Akka. Okay, this is a mandatory slide about companies using Akka and Scala, and let's just skip past that. So the word stream is kind of vague. It's a very overloaded word. If you search, for example, GitHub for streams, you will find a lot of projects that does totally different things. And I think this has kind of exploded the last few years. So one example is the Java 8 streams library, or Java 8 streams APIs in the standard library, which is essentially parallel collections or kind of functional collections. What Akka streams is something different. So let's kind of zoom in on what it means in our context. So Akka streams is a library for asynchronous back-pressured stream processing. So let's look at each part of this statement and see what it means. So stream processing. Well, in this sense, it is a tool for processing potentially infinite streams. It's a local abstraction. It just doesn't really have anything to do with distributed systems. That being said, there's nothing stopping you from using it in a distributed fashion, just like kind of any abstraction. But it doesn't provide any kind of distribution tools in itself. There is a Intel-backed project called Gearpump, which are looking into doing streams distributed from out of the box, so to speak. So in a stream, we will have at least one source of things, elements, and then we will have some kind of stages which do processing, and then they will end up in a consumer of some kind. We'll call that a sink. So we have a source, and we have things that process, and we have a sink. And of course, since I said that it might be infinite collections, then we can't really do this just having everything in memory at once, because we don't have infinite memory. So it's also about doing this in bounded memory. So next part of this sentence or statement is asynchronous. What does this mean? Well, asynchronous means that we build everything on a message-driven foundation, and we never block a thread. So whenever we need another thread to do something, there will never be this blocking on a synchronized method or something like that. So it's built around running on few threads, because you can't really do more processing than you have cores in your machine. So instead, we have kind of decoupled the processing thingy from the thread abstraction. So in this stream then, if we have asynchronicity, it means that we may have asynchronous boundaries between the different stages. So that means that the source may run in a different thread than the process, which then again might run in a different thread than the sink. This is made possible by building this on top of actors. We have realized that it's not always useful to start out in this end to make it asynchronous by default. Maybe even a majority of the streaming problems benefit from a very careful selection of where these asynchronous boundaries are. So with Akka streams, the default solution is that you explicitly demark where your asynchronous boundaries is. In the middle here is this word, two words, back pressured. Back pressure is important when we have asynchronous boundaries. And why is that? Well, because if we have a fast producer source here, which will produce 10 messages per second, and then we do some processing with those. And then in the end, we have a slow consumer, the sink, that can only process 1 message per second. Then we somewhere have to buffer these elements, right? And if the consumer is consistently slower than the producer, the buffer will fill up, and we will essentially have two options. One is to let it grow, and at some point then we will fill the entire memory, because we have a consistently faster source than sink, or faster producer than consumer. The other option is, of course, to start dropping elements. This is kind of a universal problem. So if you look at TCP, for example, this is also something that is solved in TCP and in the operating system in many places. Back pressured in this context means that instead of having the source, the producer, blindly push these 10 messages per second, we will have a way for the sink, the slow consumer, to actually propagate information that it cannot consume faster. So it will tell upstream, it will tell the stage that it can only handle 3 messages. And until it asks for more messages, it's not allowed to send more than 3 messages. So this allows us to deal with this in inbounded memory, right? So this will actually propagate back to the producer and tell the producer that it cannot produce elements in a faster rate than the far end consumer can consume. Now I showed you like a very simple linear stream, but Akka Streams isn't limited to linear streams. So you can actually have many sources, you can have feedback loops, and you can have many consumers on the other end. And all of this will be then back pressured as I described. So this makes it possible to write stream processing that is just as complex or as simple as your use case requires. So now I'm going to take a short sidestep and talk a bit about reactive streams. So reactive streams is an initiative to provide a standard for exactly this. So a standard that allows different libraries to communicate in a streamed fashion across async boundaries without running in unbounded memory. So this initiative has a large part of its origins in the Akka team and in the Play team as well. So at Lightband, we had already implemented different kinds of back pressure. We had iteratees in the Play framework, and we had negative ACK-based back pressure in Akka IO. So this sparked conversations with various people, and this initiative was started. One interesting thing might be that there is a Java enhancement process project, or whatever you call them, JEP 266 by Dog Lee, which introduces these reactive streams interfaces into Java 9. So it will actually be in Java 9. So reactive streams is a set of interfaces, and it is a specification that describes exactly how these interfaces should behave. So all the behavior that isn't covered by the actual interfaces. And often with asynchronous stuff, then it's hard to encode all the semantics, the protocol in the types. So the specification covers a lot of more things than the actual interfaces can cover. And there's also a TCK, Technology Compatibility Kit, which allows you to run a test suite on your implementation of reactive streams to see that you fulfill it. So what this actually allows for is, for example, Akka streams to interact with Vertex from Red Hat, for example. So it allows for different libraries to interact. Spontaneously, then, it may seem like this is the building block that you should build the library abstractions on as well. But pretty early in the process, then we in the Akka team realized that this would be really painful, because the interfaces of the reactive streams are deceptively simple, but to get the rules right and the implementation details is really hard. So we realized that developers using Akka streams, they wouldn't want to bang their heads, so to speak, against getting RS implementations right. So we have entirely decoupled reactive streams from Akka streams. We provide a subscriber and a publisher so you can connect to other libraries, but when you write your streams in Akka streams, you do not ever actually implement this very tricksy abstractions yourself. This also allows us to do quite a bit of clever performance tricks and such. So let's take a look at the Akka Streams API. And just like I mentioned before, we have Java APIs for all of this, and I'm going to show you the Java APIs, just the Java APIs in this talk. There's actually three different abstraction levels of APIs in Akka Streams, and we're going to look at the most simple one, the flow-based API. This doesn't allow for making these looping streaming graphs that I mentioned earlier. It just allows for pretty simple linear flows. And I think that will be quite enough if you haven't seen this before. And just keep in mind the day when you come to a point where you need to stream things back into your stream, so to speak. That is also possible. And the lowest level abstraction is called graph stages. It's primarily to write custom connectors to different other kinds of technologies, libraries, servers, thingies. Okay, so let's see if I can actually do this in 20 seconds. I'm not quite sure about that. So I already mentioned source and sink, but I said I never mentioned flow before. But these are the three primary types when you code with Akka Streams. So a source is, of course, a source of elements, and it has two type parameters, where the first one is the kind of elements that it will emit. So I have intentionally left how I created empty here. And you can see that there's a second parameter, which is not used in this case. This is called a materialized value. We will kind of skip on that for now. You don't have to understand that to get the basics. So the source has one type, which is integer, then that it emits. A flow, it will consume elements in one end and emit elements in the other end. So it has two types. In this case, we have integer, which is what it will accept, and string, which is what it will emit. And we can see here how I create it with a lambda, which just calls to string on the integer. So it's actually a graph stage that will take integers and convert them into a stream of strings. Any element that goes into it will come out in the other end as a string. And then on the kind of end of this stream, we have the sink. And the sink, it again also has only one parameter, because it will accept incoming elements. So in this case, strings. And here we have another factory method, which takes a lambda, where we just accept the string and we print it to standard output through the system out print line. And so having created these three, the source, the flow, and the sink, I actually didn't create the source, but imagine that we called something that created the source. We can then wire them together. So we do a source.via with the flow, and then we do a to with the sink. And we have now wired together a runnable graph. This runnable graph we can then run using something called a materializer. We will probably talk a bit about materialization and materializers in a little while. To make a more concrete sample, this was way more than 20 seconds. I'm sorry about that. I should have talked faster. So of course this was a bit chatty, and there was a lot of boilerplate in this sample. So there's also a lot of shortcuts to create this kind of thing. So here we have an actual we create a source.single, and it will be a stream that just emits a single value, the number 42. And then instead of creating a flow explicitly, like we did in the previous slide, we will actually just call map, which is exactly the same and just a shortcut to do that. And then in the end, we will create the sink by calling run for each, which is, again, just a shortcut to run this with for each sync that will react on every element that passes through the graph. I will have an example also of something, a sync that actually kind of leads to a return value when the stream reaches its end. So in this little sample, we have a single element source, which will emit number 1, and then it will map it to string of the number 1. And then we run that with sync.head. And sync.head, when it is executing, will consume the first element, the head of the stream values, and then it will stop consuming elements. So in this case, it will lead to a future string value, and this is represented by a completion stage, which is a Java 8 abstraction for values that we don't have quite yet, but they will arrive sometime in the future. So what you could see here was that this was completely type safe, and the types aligned. And if we would have put a flow that didn't fit in there, it would have given us a compilation error. So the source had integers, and the flow accepted integers and made strings, and the sync accepted strings. So it's this very dynamic and able API to compose streams, but it's still type safe, and you will get compilation errors when you get it wrong. Okay, I think I need to hurry up a bit, so let's do this quickly. So I told before that there's something called materialization. When we define a stream, we actually define something like a blueprint that describes the stream. We don't actually call it or run it right away. Internally, there is 2 steps, where the first one is called fusing, which take this blueprint and makes it into something more optimized, and we meld things together. So for example, if there is no asynchronous boundary added, we will actually run all of the stages in the same actor. So this allows us to make streams that are as fast as possible without introducing asynchronous boundaries, unless the user actually has said that they want to run things in parallel. And then in the end, when you have kind of materialized this flow, this stream, then you have something that you run. And this is what actually happens. This is when you actually start executing the stream. Okay, so another little side step. Let's see, I really need to think about how I use my time now. So Alpaca is a community call to arms to build connectors to give us something like a modern camel, like a reactive and asynchronous integration tool, something like Camel, where you can connect different kinds of data sources in clever ways with ease. And there's a bunch of articles in our blog about it. I can really recommend you to look into those if you're interested in this. And there already is a bunch of connectors, so you can connect to MQTT, AMQP, streaming HTTP, TCP, files, Cassandra queries, Kafka, S3, yeah, a bunch of things that you can connect. So let's dive into the first demo then. What we're going to do now is look at the source that consumes a file, and it will actually watch the file, and when new lines are added to it, those will be streamed. They will be emitted in the stream. We will then not really enrich it, but you can imagine that you would do some kind of processing as well. But we will actually then just emit those lines into Kafka server. So let's look at those sources right away. So I have a Java class here called the Kafka log streamer. which creates some configuration for the Kafka connector. So we need to tell the Kafka connector how to serialize data and what host to connect to. We then create a file source pointing to a log file called watchme.log. The file source will emit bytes, so not actually strings. It hasn't converted the strings into the bytes into actual strings because they could have any kind of encoding or such. But before we start transforming them, we will collect up till the next line feed. So we'll actually look at the bytes to see, is this position a line feed? And not until we reach a line feed, we take that data and emit it downstream. So then in the next stage, when we know that we have a full line, we convert it to UTF-8 string. And then we also pass it through a log to make the sample a bit more obvious what it does. We can actually get some hints about what is going on. So this all creates a source of strings. We then create a sink, which accepts producer record, which is a Kafka-specific type, which takes a topic and data, I think. So we have a factory method here, producer.planeSync, which is from the Kafka Reactive Kafka connector, the Akka Reactive Kafka connector. And then we take this logline source, we take every line of text in it, and we create a producer record, and we then send that to the Kafka sink. Then we have created the blueprint up to here, and then we actually run this using the materializer. So let's see this in action. I have, like the TV chefs, I have already prepared a bit. I have a half-cooked little environment here, so I have Zookeeper and Kafka running already, and I'm just gonna execute this log streamer. SPT is the D-Scala build tool, and I've kind of out of habit I have used it, but that is not a precondition to use Akka streams. It's perfectly fine to use Maven, for example. So now we can see that it logged a bit of output, and we got some info from the Kafka connection. In this directory, I have the watchme.log file, so I will just write something to it. And we can see that it was logged over here. And we can also take a look at what was written to Kafka. So let's see if I just paste this Kafka command line client entry here. We should be able to see that samples that just work. Yeah, that was a bit too optimistic, I guess, to actually believe that I could pull this off. Okay, let's just move on because oh, now we got stuff. Okay, so here we can see that that my entry LO vjug24 was written into Kafka from the writing side, which was the Akka stream, and then we have the command line client for Kafka, which just now wrote this entry, and it also wrote a bunch of earlier entries which I have written into the Kafka topic while preparing this session. Okay. So what we had here, which was maybe not so obvious then, was that as we have back pressure all the way from the sink, then the amount of data that the Kafka server we are pushing data to can handle, and the amount of data we can push across the network to it will back pressure all the way back to the file watching source. So if the network is slow, then we will not actually consume data from the file until we actually have time to process it on the sink side. Okay, so let's look at another sample. So now we will be instead the consumer that consumes from the Kafka topic, and we do some kind of processing. In this sample, bot detection. And it's written here, clustered consumers. So this is an example where Akka streams being local, but it's perfectly fine to, for example, run the streams on every node in the cluster to manage the distribution, and then have Kafka solve. So Kafka has functionality to allow for multiple consumers of the same topic. So we will use the same group, for example, and this will allow us to scale out an application that does streaming, even though the streams in themselves doesn't really support this kind of distribution or scaling out. So let's look at that next sample then. There's the Kafka bot connector. So I'm going to skip through this a bit faster. Just like the other sample, we will create settings that tells us how we connect to the Kafka server. We will then create a Kafka source using consumer.plain source with the settings, and we also send in which topic we want to subscribe to. We then take the source, we run it through a parser of some kind, which will give us a failed or a successful parse result. So we then, in the next step, we throw away all the unparsable ones. You will probably want a more clever kind of strategy to deal with bad data, but just as an example, this will do. And we will then pass each element, which is a tweet in the sample, to a method which will look at it and try to detect if it is a bot or not. And then we get a bot detection result out of this method. And then we filter, so we only have the ones that are bots. And then we do something pretty cool, which is really hard to do with kind of other technologies maybe, or at least in my experience, this is not something that is as smooth as this. So grouped within will either group elements that arrive within 1 second, or will group at most 100 of them as a list. So it will, for every element that drops in, it will start appending them to a list. And if a second passes, then it will emit that list of elements downstream. And then we have this 100 upper limit here as a kind of bounds stopper, so that we don't create infinite or really huge lists, but those will be emitted one at a time. Those lists we then pass to the write bot report method here, which will in this case just do a print line standard out. So this will actually then write some information about the elements that was detected to be bots. Okay, so I'm not even going to run this actually to kind of have time to look at more stuff. Okay, to be able to show you like the last sample, I need to take another detour into Akka HTTP and tell you a bit about how that is connected to Akka streams. So Akka HTTP is built on top of Akka streams. So everything or a lot of the things in Akka HTTP is modeled using Akka streams. This means that a HTTP server in Akka HTTP is a flow of incoming requests and outgoing responses, right? The body of a request that comes in is a source of byte string. So it's the actual bytes of the request is streamed. This might seem maybe just complicated at a first time you see it. it has some really cool implications, or it makes some really cool things possible. So this is what we're going to try to demo in the last sample. But I'm going to try to give you an overview of it first. So in this case, we're going to have a source of tweets of some kind. So we're pretending that we are building the next Twitter. Incidentally, also using the concept of tweets, which might not be the best idea if you're going to build a Twitter killer, so to speak. So the source will emit things to a flow, and that flow will be some kind of higher level abstraction. And then it will actually be streams, Akka streams, all the way down to the TCP connection. So we will stream tweets, and those will end up as chunks of bytes, which will be put out into the operating system socket, where there is a buffer. So if the receiving side is kind of busy and doesn't ask for more, then the inherent built-in flow control in TCP will actually back pressure so that the OS buffer fills up, which will back pressure into TCP, so that the streams TCP, so that it actually back pressures all the way to our source. So this is really nice. It allows for bounded memory streams processing across HTTP and network. So this is what I'm going to try to show you now. This is the kind of the big demo of this talk. So what I have prepared is a little application which will stream tweets, which is a local little class here with just a text in them. So something a bit simpler than a tweet, probably. And to make things really easy to understand, we're not actually connecting to a database or anything, but we're going to have a source that repeats a single element as many times as the downstream wants, so to speak. To get some kind of insight in what happens, we have a map here which doesn't really transform the tweet into something else, but it sneaks in a log entry in between, so that we can show that we can see that it actually generates a tweet, that a tweet is streamed downstream. Then we have something called a route, which is the Akka HTTP DSL for defining web service endpoints. So we just say that if there is a request to the path tweets, then we complete that request with this source that we have, right? So then we will actually stream these tweets, and we will first convert them using a marshaller into JSON. We will stream that JSON to the client when it connects to this tweets URI. We take this route and we create a flow, and we take this flow and we give it to HTTP bind and handle like this to actually start the web server. So this is all of it, essentially. It's a very short little application. So I'm going to go ahead and start this in a terminal. And we can see how it probably compiles now. It just starts. And we have the HTTP application running at port 8080. So I can connect to it using curl, localhost 8080, and then tweets. And we can then see that it streams this JSON chunks as like crazy. Okay, and then I'm going to start a netstat application here. So I have prepared a little script called print OS buffers. So here we can see the connection from both sides. We have the client and we have the server. If I now take this HTTP client and I pause it. So in Unix, we can pause a process using Control-Z. And we can see how the buffers filled up. And we can also see how the server stopped actually producing any elements, right? And if we now take this process back into running, we can see how the server starts processing output again. So of course, in this sample, it wasn't super interesting because we're generating these, but imagine it would be a database result, for example. So we would select all the elements in this huge table. And as long as we can stream them from the database server, that they aren't sent in one huge chunk, but in smaller chunks, then this back pressure will work the same all the way back to your database server. So this is some pretty cool stuff. The back pressure working all the way from the HTTP client to our source. And if you look at the code, there isn't really any specific logic that talks about TCP back pressure or anything like that. So you essentially get all this for free with the abstraction. Okay, I would say that demo just worked. That is good. So Akka is a open source project. It's Apache 2 licensed. We have a large community, but we love to have an even larger community. So we have tried to mark up tickets in our issue management system that are easy to contribute. If you want to join in and write a small feature or make a small bug fix, then you have a few links here. First two, which gives you a smorgasbord of nice tickets that you could help out with. If you're not interested in helping out, then we have the mailing list and the chat rooms, which will help you get started. We also have this Akka Stream Contrib, which is kind of higher level connectors. So for example, the file source that I showed you in the first two samples, or the first sample, is available from this Akka Stream Contrib project. Yeah, what isn't in here is, of course, the Akka homepage, which is akka.io, where you can find a very complete set of documentations for all the different parts of Akka. So that's it. There's a link here to the samples that I showed you, and also some contact information if you would have any questions in the future. But then probably better to go to the Gitter channel or the mailing list to get help from the entire community rather than just getting in contact with me.
Okay, awesome. Thank you very, very much, Johan. And we have a question straight in on IRC from Brett W. Regarding back pressure, is the source of messages, if the source of messages is an external system and it's producing many more messages than the stream can handle, what happens to all the messages that cannot be processed? Are they skipped, or is there a strategy?
So this depends on the connector, so to speak. There was a slide with links to blog articles. I would, in the middle of the presentation maybe, where we talk about how you can deal with different kinds of blocking and kind of legacy connectors. But in general, of course, you will try to back pressure, to not accept more messages than you can handle. And then you can even that out with buffers, for example. If you have a spiky actual source of elements, then you can deal with that with buffers. But if you have a consistently faster source than consumer, then and have no way to back pressure that, yeah, then you will have to drop elements or such. But that is not like a general thing, but it will depend on the specific connector to this technology that you're using.
So it's more about throttling the input rather than dealing with the...
Yeah, exactly. And I mean, since if you're doing it across network, then you always have TCP, and you can essentially always actually back pressure TCP and not accept more data.
Okay. Any other questions from the Pakistan jug?
Hi.
Hey.
Yeah, I mean, I've seen Akka for first time over here. I haven't discovered it otherwise. But from where I've seen from this talk of yours, it seems very similar to Erlang. Have you guys, I mean, explored Erlang? I think whatever feature Erlang gives us, they are kind of implemented in Akka now, like actor model and this fail fast and all this stuff is inside Erlang built in, right?
Yeah, that is correct. So Erlang was the inspiration for Akka originally to write something like Erlang's actor model implementation, but for the JVM, right? So you could use it with Java and Scala. Streams provide something that isn't really in Erlang as far as I know, which is back pressure then. So I might be wrong about this, but what I have seen is Elixir, which is a language on top of Erlang, where they have added constructs that are similar to how we do back pressure, but inspired by talks with Conrad, actually, my colleague.
Any other questions?
No.
Okay, so I'll just check IRC. I think we're... Okay, so that's all the questions we've got. And in fact, that actually concludes APAC. So we're a third of the way through this conference now. So a couple of things before we switch across to EMEA.